Hi, I am Rohan Kundu and welcome to the presentation on post-quantum cryptography and its application in smart city. A little bit about myself. I am currently a PhD student at Lund University in the Department of Electrical and Information Technology under the Secure and Network System Division. My research is funded by the SMARTY project, also known as the Secure Software Update Deployment for Smart City, funded by the Swedish Foundation for Strategic Research. I am jointly mentored and supervised by Martin Held, Elena Pagni, and Nikolai Paladi. My current research interests include secured cloud storage, post-quantum cryptography, and lattice-based cryptography. So, what is post-quantum cryptography and why it is important in the concept of smart city? So, before going into the details, let us try to understand a very practical and simple day-to-day life situation. Every day, we use various secured websites like Bank ID Swish and other websites for banking, sending money to friends, shopping, and accessing health related services. In this website, we share various sensitive information related to our personal data. But what will happen if one day these websites are no longer secure? This could happen with the advent of quantum computer, which is a very complex and powerful computing device which can solve some computational problem in seconds which take a classical computer for ages. But with the upside comes a downside also. A quantum computer, or rather a practical quantum computer, could break the current encryption system that secure all our data, creating a huge data breach. This is actually the primary motivation behind post-quantum cryptography, so that we have a framework of secured crypto systems which could protect our data even if there is a quantum adversary. In order to understand a basic difference between classical computer and quantum computer, it is important to understand the difference in their building blocks. A classical computer has only two states. A bit is formed of mainly two states, that is the zero state and the one state. And quantum computers are a hybrid of zero state and one state, which are known as qubit or quantum bit. This is actually a linear combination of both 0 and 1. These are known as the quantum state, and the principle through which you achieve this state is known as the superposition principle. Because it can have so many values, this increases the computational ability of a qubit in comparison to a regular bit. The public key encryption algorithms that we use in our daily life to encrypt our data are RSA, elliptic curve digital signature algorithm, Diffie-Hellman key agreement protocol. These are all standardized algorithms. But with the advent of a quantum computer with a quantum adversary, these algorithms will no longer be safe. A well-known mathematician, Peter Shor, has proved that by creating a polynomial time quantum algorithm, the RSA and elliptic curves and Diffie-Hellman could be broken in seconds. This could be really dangerous and can cause huge data breach. So it was the need of the hour for mathematicians, cryptographers, and scientists from all over the world, as well as from the cybersecurity community, to come together in order to create a framework for post-quantum cryptography. So people in NIST, or the National Institute of Standards and Technology in USA, came together in order to create a framework for quantum secure future, which are mainly based on assumptions like lattice-based, code-based, multivariate-based, hash-based, and supersingular isogeny-based. Today, right now, we will discuss only about the lattice-based, which is one of the leading assumptions for post-quantum cryptography. So in order to understand the current situation, it is also quite interesting to see the current status of the NIST post-quantum submission. Out of the 82 submission that has been submitted in 2017 in the initial round 1, today we have the top 4 finalists for the public key encryption algorithm, which are post-quantum secure. The leading one is the NTRU, which is lattice-based. Then we have classic Macaulay, which is code-based. Then we have Crystal Kyber, which is again lattice-based. And finally, we have Cyber, which is again lattice-based. So it goes without saying that lattice-based cryptography is of quite an important candidate when it comes to post-quantum primitives. Now, one may ask why lattices are so important, or what is about lattices. So mathematicians ask themselves a very simple but yet very important question, that whether they can create public key encryption out of lattices, which are quantum secure, and the answer was yes. So what are lattices? You can imagine lattices like a 3D structure. In 2D, one can imagine it like a mesh. In 3D, you can visualize it like a cube with all the points which are equally distributed among each other. One can define the basis, and also taking any random point inside a lattice, one can define a vector. Mathematically, lattices can be defined as a linear combination of bases where the coefficients are from the field of integer. Now that we know a little bit about the lattices, it is important to understand that how lattices and lattice-based cryptography are linked together. In order to get a cryptographically hard problem, we have to create some computationally hard problem on lattices. The major two types of problem that has been proved to be difficult against quantum adversary are shortest vector problem and the closest vector problem. It has been proved that even if there is a quantum adversary, it is not possible to break these two computationally hard problem that has been defined over lattices. Let us now talk about the Internet of Things devices, which are the building blocks for a smart city. Each and every devices that we use right now in our daily life, from mobile to computer to internet router to smartwatch, which are connected via the internet and share data in return, are all part of the IoT. These devices collect a huge amount of personal data, which are in turn stored in a third-party cloud storage provider. This cloud storage provider then in turn send this data to the particular service provider. We all know about the current threat and security vulnerabilities posed by storing sensitive data in third-party cloud storage. So it goes without saying that with the advent of quantum computing, the threat is imminent. Let us now talk about how the post-quantum cryptography plays a role in smart city. With everything becoming more interconnected and the network complexity increases, it is important that we move towards a more resilient and privacy-focused method. That's why we propose to embrace the new technology of blockchain, which is a peer-to-peer distributed ledger, in order to achieve the security goals. So, in a blockchain, a transaction is recorded as a block of data as a step one, and in the next step, each block is connected to one another before and after it. Finally, the transactions are blocked together in an irreversible chain so that nobody can change it. Following are the properties that makes the blockchain technology so attractive in order to gain the privacy goal that we want to achieve in a future smart city, mostly because of the decentralized nature, anonymity, non-fungibility, and transparency. By non-fungibility, we mean that it is very difficult to immute any data that are being stored in a blockchain because of a concept of one-way hash function. So it is a very eminent question to ask why lattice-based protocols that we discussed earlier are best suited for the IoT security. These are for the following reason: because of strong security guarantee, high efficiency in compared to the other post-quantum assumption, wide applicability in terms of industry adoption and implementation, and also smaller key size in compared to code-based and hash-based primitives. It is also interesting to note that lattice-based scheme like New Hope has seen wide-scale industry adoption from Google and Infineon. So it is quite assuring that not only it is a research-intensive protocol, but also it has commercial success. Since we have discussed about post-quantum cryptography a bit, now it is time to discuss about quite a new concept known as the post-quantum blockchain. In a smart city, we not only revolutionize the mobility sector, we also revolutionize our contemporary financial sector. In a smart city, it is believed that people will have more power and do not have to rely on a central authority. This can be achieved through decentralized finance or DeFi. These are highly based on blockchain protocols like Ethereum and Bitcoin. We have seen in the past decade how Bitcoin and other blockchain peer-to-peer networks like Ethereum has shaped the global financial system. But it is also important to note that these blockchain projects, the security of these blockchain projects are based on pre-quantum assumption like the elliptical digital signature algorithm. Under a quantum adversary, the security of this pre-existing blockchain could be in danger. This gives rise to a fairly new concept which is interesting in both research as well as commercial terms known as the post-quantum blockchain. So, we try to give a quite a futuristic approach in understanding how post-quantum blockchain could be an integral part of our future smart city. Since each and everything of our day-to-day life are interconnected, causing more efficiency, easy lifestyle, but at the same time, with high complexity comes security threats. Since if one of the component in this highly interconnected network gets corrupted, the other networks will also get corrupted equally. So, a blockchain technology which is being used in a smart city concept when comes under a quantum threat could cause severe security issues. It is interesting to note that the blockchain technology is based on proof of work in which a client can work as a miner who can publish a block by solving a mathematically hard problem which is hard to solve but easy to verify so that each and every node of the block can verify the computation and include the block into their ever increasing chain. But the proof of work will not work under a quantum adversary because those are created with pre-quantum assumption. So it is time to make proofs for blockchain which are quantum secure. There has been a research going on in having post-quantum signature algorithms like lattice-based instead of elliptic curve digital signature algorithm to make the previous blockchain quantum secure against any adversaries which are able to have access to quantum computer. So This is a very new area of research, and we think the future holds in creating a post quantum blockchain which could be highly scalable and used for future smart city concept. Thank you.